Hello everyone and welcome back. So today we continue our discussion on GPU programming and CUDA, and in particular we are going to talk about two-dimensional data. But let's have a recap from the previous lecture. So we know that we have a CPU and a GPU in our system. The CPU has its own memory, which is called the host memory. And the GPU also has its own memory, which is called the device memory. And you can also send data back and forth between the host memory and the device memory. So usually in a CUDA program for to be executed on these systems, the first thing that you need to do is to allocate some memory on your GPU. Then you copy the data from the main memory or the host memory to the GPU memory. You perform computations on the GPU, and then you copy the data from the GPU to the CPU. Usually, what we send from the GPU to the CPU memory is the results. And finally, we deallocate the GPU memory. So this is the basic workflow when you work with both CPUs and the GPUs on the same machine. So we had a one-dimensional example. So we talked about the grids that are run when you execute a kernel. So when you execute a kernel in CUDA, a grid of threads or a grid of thread blocks are executed simultaneously and at the same time. And within your kernel, you could have different built-in variables to access the thread in the grid. So you have the grid dim, which gives you the number of blocks in the grid. You have the block index, which gives you the index. For example, in this case, the index of the block along the x direction. Then you have the thread ID along the x direction and the block dimension, which is the number of threads along the x direction. So this is a one-dimensional example. In CUDA, you can have at most three dimensions for the blocks and also for the grid. So you can have a cube of thread blocks, and in each thread block, you can have a cube of threads. So then we had an example for a parallel vector addition where you assign each data element to a thread, and then you perform the addition operation in parallel. And here is how we developed the kernel for this vector addition, which is called vector addition kernel, in which you pass in the vector x, y, z, and the number of elements. Then you need to find the corresponding index for your thread that is responsible to perform this computation. So for example, we find the index of the thread that we want to work with, and then we assign this task, which is a simple sum to that thread that we identified. So as I mentioned also, we might have more threads than the actual elements. So then you need to always check the boundary conditions. So in this case, with this if statement, we made sure that uh, the threads that we don't need them to perform some computations, they just ignore this computation here. Okay. All right. And then we talked about the compilation. So you usually write your CUDA and C++ code in a .cu file in the simplest case. Then you call NVIDIA CUDA compiler to compile your code. This compiler sends the C++ part of your code or C part of your code into a C compiler, and then you have the normal compilation flow, and then the compiler generates a binary that can be run on your CPU. And in the GPU part, you first compile your program into .ptx files, and then you have a just-in-time compiler that compiles these PTX files into device assembly, and finally an executable that can be run on your GPU. All right, so we have the same thing for multi-dimensional data as well, which we are going to talk about uh, now. Okay, so let's talk about multi-dimensional data and how we can work with CUDA when you have multi-dimensional data, such as images and videos, things like that. Okay, so I try to explain uh, working with multi-dimensional data with two examples. The first example is RGB to grayscale, where we want to make a colored image to like transform a color image into a grayscale image, as we can see here in this slide. So for parallelization, what we do is to assign a thread to each pixel in the output image, and that thread is going to be responsible for transform the RGB into the grayscale. So quite simple. As I mentioned, CUDA supports multidimensional grids, and it is introduced in CUDA because when you have multidimensional data, it's gonna be easy to map your threads to the data when the thread structure is kind of aligned with your data, with the structure of your data. So it basically simplifies the processing. So for example, you have an image like this, and then if these are your pixels, then you can assign a thread block to a patch of pixels, right? So in a like a two-dimensional manner. So in this case, we have four thread blocks, and within each thread block, we have a thread assigned to work on a pixel on this image. Okay. So first, let's talk about how we actually configure the grid of thread blocks in this case. So you should use a variable called dim3, which is available in CUDA runtime header file. So with this dim3, you can define the number of threads per block. So in this case, our block has 32 by 32 threads. So 32 threads in like in a row and 32 in columns. So it's a two-dimensional block. And then, similar to what we had before, you can compute the number of blocks in your grid, both in X direction and Y direction. And then, when you write your kernel, you can execute your kernel using this syntax. Then, for the number of blocks, you pass in the number of blocks that you defined here, and then the number of threads per block. So this is similar to what we had before, but in this case, instead of just passing in a number, you pass in a dim3 type to make sure that you have, in this case, a two-dimensional grid of threads. Okay, so let's see what exactly we want to do. So if you remember, in the one-dimensional case, we had some built-in variables to identify the thread that you want to work with. And in two-dimensional case, also we have a similar thing. So let's see how we can use that. So in this case, we have grid dim .x for getting the number of blocks along the x direction. And also we have the grid dim.y, which gets us the number of blocks along the y direction, right? So for the blocks as well, we have x and y. So we can use block ID x to get the block index along the x direction. And if you use .y here, you get the block index along the y direction, right? And then you have this block dim which gives you the number of threads along the y direction if you use blockdim.y, and then you have this blockdim.x if you want to know the number of threads along the x direction within that block. All right. So you have also the same thing, same terminology for the thread index. So you have thread index, thread ID x.x to know the index of your thread along the x direction, and then you have a similar thing using that y for having your thread index along the y direction. So, and if you have a three-dimensional grid, then you have x, y, and z. So you have three variables in those cases, and this is the maximum dimension that you can use in CUDA. All right. So let's see how we can write RGB to gray kernel to transform a like colored image into a grayscale image. So first, we use this global keyword as we had before to specify that this is a kernel and this is my kernel name. And in this particular example, we pass in the red channel, the green channel, and the blue channel of the image separately, but you can also have it in one array. Then we have an array for storing the grayscale image, and then we have the width and height of the image, right? So these are the parameters that we use in this kernel. So similar to what we had before in the one-dimensional case, we need to identify the thread that we want to work with. So in this case, because our data is two-dimensional, so we need to identify our thread along x and y direction. So here we use the same equation for identifying the thread in the row direction, which is y, and then we use exactly what we had before for identifying the thread along the columns, right? So the column index and the row index of the thread that we want to work with. And then we work on the image, right? So the first step was to identify the row and the column index of the thread that we want to work with. And this row and column is within the thread block. Okay. All right. So before uh, talking about how exactly we write the conversion logic, so let's have a short review on how C stores multi-dimensional or two-dimensional arrays. So in C, we store multi-dimensional data or multi-dimensional arrays in a row major order. So it means if you have a two-dimensional array, what C actually does is to store them in a linear array. Actually, it should be familiar from your first homework assignment. So what it does, it first stores the first row, and then the second row, the third, and finally the last row. So although your data is two-dimensional, the way we store it in the memory is one-dimensional. So it is called like linearization of two-dimensional or like high-dimensional arrays. So then if you want to know the index of your element in this two-dimensional array, like when you use this one-dimensional one, you just need to like use this formula. So what you need to do if you want row like this row and this column, like here, then you just need to multiply row by the width of the image or the number of columns, and then you sum it with the offset, which is the column index that you want, right? So this index basically gives you, if you name your array to be A, row, and column, something like that. Okay, so we use the same thing in our kernel as well. So what we need to do to convert each pixel, so after identifying the column index and the row index of the thread that we want to work with, using this linear indexing that I talked about, we just need to use this equation, which is quite popular in image processing, to convert a colored pixel uh, into a grayscale pixel, right? So this is how exactly we write this we write this kernel. So later I'm going to show you a live demo and a slightly different implementation for the same problem. But this is the main logic that we're going to use. Okay. So as before, we need to check the boundaries of the image because we might introduce more threads because of the number of thread blocks. So we don't want these threads to do anything because they're going to be out of image boundary. So here, similar to one-dimensional case, we just need to check if the thread index row is smaller than the height, and thread index column is also smaller than the width of the image. Then we have this converting that we had before. Okay. So you might ask whether or not our kernels are that simple, but no, because it actually depends on the problem and the processing that a thread should perform. So here is another example, which is slightly more complicated than this color to grayscale conversion, which is called image blurring. So in image blurring, we want to keep the main feature of our image, but we want to make it blur. So basically, how we can do that is we just need to compute the average of the corresponding input pixel and the pixels around it, right? So this way you can, this is one of the ways that you can make an image to be blurred. So as we can see, this is the original image and this is the blurred version. So what you need to do, as I mentioned, you just need to average each pixel with some pixels around it. So in this case, assume this is our image and these are our pixels. So in the output blurred image, this pixel is computed based on the average value of the pixel itself and the surrounding pixels. So this kind of application is quite simple to parallelize. To do that, similar to the previous case, we assign a thread to each pixel in the output image, right here. And each thread is responsible to compute the average of that pixel and the pixels around it in the input image. And then it writes the computation output into this pixel that it was assigned to. So let's see how we write the kernel for this application. So again, we start with this global keyword to specify that we are writing a kernel. Then we return nothing, and this is the kernel name. So in this case, you just need to pass in the image. So in this case, we pass the image like with RGB together, and then you need to pass in an array for the blurred version and the image width and the image height. So similar to the previous example, the first thing that we need to do is to identify the column and row of the thread in the thread block that we want to work with. So in this case, we call it out row and out col because we are working on the output image row and column. So we identify them as before. Then we have this boundary condition because we don't want to be outside of the image boundary. Then we define a variable for computing the average, right? And then we write two for loops to look around the pixel that we want to compute the average. So in this case, we define a blur size variable, which can be a global variable. And this blur size uh, tells us like how many pixels we want to consider around our image. So basically, we are looking for a square with this blur size width. So in this case, we just need to compute the average, right, for the uh, for the pixel that are within this square, and then we compute the blurred pixel using just computing the average. So sorry. So here we compute the sum, and here we are just dividing the sum by the number of pixels that it computes. That can be obtained using this formula. So I'm going to show you a slightly different implementation in a minute, but this is basically what you need to do. But there is a catch here because uh, you know, although our threads are within the image, but depending on the blur size, we might get out of the image boundary again, right? So in this case, if I'm working with this pixel, so I have these pixels as well, right? But these are outside of my image when I'm working with these corner cases, like here, 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 right? So I need to provide another boundary condition to avoid these cases as well. So that's why in the final implementation, we have another if statement here to make sure that uh, we are still within the image boundary. Okay, you just need to make sure that the in row and in col, which is the index of these uh, pixels, to be inside the image boundary, right? So you check it like that. All right. So this is how we work with this image blurring application. So in a minute, I'm going to show you a real implementation using my VS Code. All right. So the final example, which has nothing to do like with the image at the moment, is the matrix multiplication. And I will talk briefly how we can perform matrix multiplication using CUDA. So in this case, we want to compute the matrix C, which is obtained by this A by multiplying A and B. A and B are in this case n by n matrices. So in this case, C is going to be also n by n, right? Because A is n by n. So B also is n by n. So C is n by n. So this is a special case of general matrix multiplication. So in this case, each element in C can be obtained by dot product of rows of A and column of B, right? So if you dot product this particular row and this particular column in B, you compute the value of this element in the output matrix C. So similar to what we had before, for the parallelization, we can assign a thread to each element in the output matrix. So in this case, for each element, we assign a thread, and that thread would be responsible to fetch this row, for example, this thread I'm talking about to fetch this row from the memory and also fetch this column from the memory, perform the dot product, and then write it into this C matrix. So as you saw in your second homework assignment, we can also perform cache optimization here, but at the moment we just focus on this like naive parallelism approach where you just assign a thread to to compute the output element without like thinking about cache optimization. Okay, so the kernel in this case is quite simple. Again, we start with this global and then the kernel name. So we pass in a linear arrays for A, B, and C matrices, and also the number of elements, right? And then we again identify the row index, the column index of the row index and the column index of the thread that we want to work with. And here we perform the actual dot product, right? You just need to loop through the row of A that you want and the column of B, right? Using this linear indexing. And finally, after you computed the dot product, right, you can write it on the output uh, matrix. So in this case, we computed the dot product all, like sequentially by each thread, but within this kernel, you can also parallelize this dot product, but we're not going to talk about that. So this is a very simple matrix multiplication kernel in CUDA. All right. We didn't check the boundary condition. Again, we always need to check that because, as I mentioned, the number of threads and the thread blocks might not really fit the number of elements in our matrix. So you just need to perform like this boundary condition check by just introducing a simple if statement here to make sure that your rows and your column in the output matrix are are within this that are within the output matrix C. All right. So these were just simple examples on how working with two-dimensional two-dimensional data. And I'm now going to show you how we can write these applications in VS Code and how we can compile them and how the entire code looks like when we want to write these things. Okay, so let's do that.